Okay, AP Physics 1. So, we're about to start the lesson on Unit 0, Exploring Relationships. Now, the reason why this is Unit 0 is because it's actually pre any true physics content. Exploring relationships is something that we do in science as a whole, but it involves some skills that we definitely need in particular on organizing and analyzing data to be able to explore them effectively when it comes to this class. So what exactly are we talking about when we say exploring relationships? What relationships are we talking about? Well, in most sciences, whenever we're doing any sort of investigation, we're usually trying to look between one variable A and one variable B, no matter what they are, and establishing how are these two connected. If you alter A, how does B change? Or if B is changing, how do we know A must have been altered? So these relationships between variables, we often are going to represent with something called a mathematical model. And it's called a model because it is an approximation or a simplification of reality. And usually, this mathematical model will lead us to an equation that demonstrates the relationships between these two variables. But before we go any further, these should be terms you are very familiar with, but just to make sure, remember that there are two types of variables we're commonly going to see: independent variables and dependent variables when we look at these relationships. And the independent variable is the cause. It is what is causing the dependent variable to change. Now, typically, in a lot of these investigations, the independent variable is what we are directly controlling. Whatever we are physically changing ourselves from trial to trial. However, another thing that is often the independent variable is time. And although we do not control time, time is always independent of anything else. It's going to keep on marching on no matter what. The other type of variable is the dependent variable, or the effect. It is what depends on the independent variable. So when the independent variable changes, the dependent variable then changes as well. But when we are investigating the relationship between two variables, we're going to do some sort of a laboratory experiment to get some data on how they are connected to each other. And we'll talk about that later. But how do we go about organizing this data once we have it in order to eventually lead us to establishing that relationship for sure? Well, there's a couple different ways we do it. The first one is typically data table. Pretty straightforward. You have one variable, you have a second variable, and we have our two lists of data. Now, it doesn't matter which column is which one's the independent, which one's the dependent. No, that does not matter. However, there is something very, very obviously missing here, and that is the fact that we do not have units on this table. Now, I'm going to go ahead and write those in here. So S and J. You don't need to know what these units are. That's not what's important. This is just an example. But I want to be real clear here. No naked numbers. I cannot emphasize this enough. At no point in this year should you have a number that does not have a unit. There's a very few exceptions, but more often than not, all numbers need to have units, or else what does it mean? Is it meaning seconds, or minutes, or meters, or grams, or kilograms, or whatever? Without a unit, numbers are meaningless. Okay. Additionally, we are going to create a graph. Sorry for writing through that, but that's okay. Now, a couple things we want to establish here about graphs. First off, if you're hand drawing it, you always want to have it on gridded paper or graph paper, and typically you want the graph to be pretty big. Now, the reason for that is that when you're hand drawing it, when you're trying to analyze things, if it's too small, you're not going to necessarily notice all the details. That is less important for a computer-generated graph, but for a hand-drawn graph, you want it to be quite large. Additionally, always use a straight edge when you are hand drawing these. Otherwise, they get real sloppy real fast. Okay, now a few other things we need to make sure that we have here on this graph. So first off, we have U and T here, and I know you don't necessarily know what those stand for. I'm going to go ahead and give you a hint. T is time. So T is going to be our independent variable. and u is going to be our dependent variable, and our independent variable always goes on the horizontal axis. So I'm going to write t with a unit, always have to have a unit, and on the other axis I'm going to write u with a capital J. Once again, always have to have a unit. Additionally, so these are our axes labels with units, we also need a title here, and typically speaking, how this is always written is dependent versus independent. So we would title this as u versus t. I know that seems a little odd, but that's just the formulation. That's just the way it's done. Okay, lastly, and possibly most importantly, is the scale. Now, I feel like students more often than not, when they mess up a graph, it's the scale. It does not need to be complicated. Okay, now first off, we always, let's go ahead and get a different color in here. Let me just go with black for a second. Always should have 0 on here. Now, sometimes, I know you've learned how to do like little breaks here so that you can skip ahead to a higher number. You don't want to do that more often than not. The reason being because that might mess up the trend of the data and might make us have some issues when we're trying to analyze it properly. Now, when we're trying to figure out these scales, please use simple numbers. All right, and you want to make sure you're always using at least half of the grid space for the entire plot. So t goes from 1 to 5, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so a nice simple way would be, let's do every 2 is 1. So this would be 1, 2, 3, 4, 5, and I can even get fancy and write a 6 there. All right, and then this other one goes up to above 16. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now, people are often tempted to be like, oh, well, if I do 1.6 for every, grid line, then this will be exactly 16 and I'll use the whole space. Don't do that. Go with nice, simple scales. 1s, 2s, 5s, 10s, 0.5s. Nothing crazy, or else you're just really going to screw yourself up. So let's go ahead and say, let's make this actually, let's do 4. Yeah, so it's going to be 2, 4, I'm going to do by 2s. 2, 4, 6, 8, 10, 12, 14, 16. Perfect. Good enough. All right, that's all we got to do here. All right, now let's go ahead and graph these points. Let's make this a little bigger. And so we've got 1, 7.5. That goes right about here. I have 2, 10.1. Okay, so this is right about there. I have 11.73, which is roughly there. Oh, a little bit higher. There we go. I have 4, 14, right on the dot. And I have 5, 16.3. Now, another thing to be aware of. This is a perfectly acceptable graph. Do not draw some sort of line connecting these, because this is not an accurate representation of your data. What is accurate are simply the points. We just want the points, nothing connecting them. We're going to get to that why in a second. Now that we've plotted our data, we've organized it into a plot, a graph, how can we analyze it to figure out this relationship? Well, typically, if it is a linear line, which this one is pretty darn linear, we can use a line of best fit, or a best fit line, which will display the trend of the data. Now, when we draw this, usually you're going to use a straight edge. You're going to get a ruler or something like that and draw it on using that ruler. And when you're trying to get it right, lined up, you want about half the data points above the line, about half the data points below the line. We really don't need to be more precise than that. However, we need to be real careful. Do not force it through the origin or your 0 point or any of the specific data points. For instance, let's go ahead and say you drew one straight line right there. And this goes through the origin, but this is clearly not following the trend of the data. It is horribly skewed because the origin is nowhere near this trend. So let's get rid of that one. Let's try another one. Now this is closer, and in fact, I would say this is pretty close to acceptable. The only thing I would say that's kind of an issue, well, one, I'm glad that they're not really touching any data points. but I'm a little bothered by the fact that all of these data points here are below, and there's only one above. So close, but no cigar. Let's try it one last time. That's pretty good. So if we look, we've got, it's touching a couple, but it doesn't have to. It doesn't have to touch any data points, in fact. But it is pretty close to all of them. We have about half above and about half below. Well, now we've drawn our line of best fit. We need to be able to write an equation for this line, because that equation will tell us the relationship between these two variables, u and t. Now, I want to be very, very careful here. When we do this, we don't care about the data points anymore. This trend line is now basically representative of our data set. The data points themselves just helped us draw the trend line. Now we can just pretend like they don't exist, because the trend line is showing us the real trend. So to write the equation here, okay, so it's going to be a typical equation of a line, y equals mx plus b. So we need to know the y-intercept, and we need to know the slope. First off, in regards to the y-intercept, just eyeball it. So for instance, I went ahead and circled that point right there, and it's about 0 to just above halfway between 4 and 6. So I estimated about 5.2. Right? Now, we don't want like a crazy number of decimals. We should never have more than 2 decimal places. And 5.2 really is about as precise as we can get. That might even be a little too precise. So about 5.2. And we're just going to eyeball exactly where that lands on the graph. This is why we don't want a break here. Because if we have a break and this hits below the break, all of a sudden finding the y-intercept can be a real hard thing to do. Additionally, though, we need to find the slope. Now, you all should know how to find the slope of a straight line. You pick out 2 points on the line, and you use this very, very common equation. Slope is equal to y2 minus y1 over x2 minus x1. But which data points should we pick on this trend line? First off, and this is key, do not pick the little orange data points here. You want to pick points on the trend line, not the data points. And why is that? Well, that's because if I pick, like let's say for instance you picked this data point here and this data point here, I would have a line going through these. I'd find the slope between these 2 points, but that's not really the slope of this red trend line. That's the slope of only those 2 points. And so we're no longer taking the entirety of the data into account. We're only taking those 2 data points. So don't pick our data points. Pick points on the trend line that are not data points. Specifically, it's really easy if you can get once a hit on the grid lines. That way you know you're really precise. For instance, I have one right here at 618 and one right here at 210. And that looks like I selected a data point, but I actually didn't, because this orange data point was 210.1, and actually the line goes right through the grid point at 210. Let's say you didn't have perfect grid line spots like this. Another good one would be like, for instance, right here. That's about halfway exactly in this mark. You don't want to pick points like this. They're in the middle of like a grid box. It makes it very hard to analyze. Okay, so I plug in my numbers. I have 18 minus 10 divided by 6 minus 2. If you do the math, if you need to, feel free to grab your calculator, which I don't have right next to me at the moment, but always feel free to use that. You get 8 divided by 4, or a slope of 2. So now we have the information we need to write the equation of this best fit line. And you might be thinking, okay, well then I know what to do. I'll do, let me use green, why not? I'll do y is equal to 2 for the slope, x plus 5.2. Close, but no. And there's a couple reasons for that. So you are right in thinking that we want in y equals mx plus b form. But there is no x and y in this plot. This is not marked x, and this is not marked y. X and y can mean very specific things, and typically, in this equation here, x and y are just placeholder variables that we're going to replace with real, meaningful, physical variables. So specifically, I will replace x with t, and I'll replace y with u. Additionally, while it was good to put in 2 here for the slope and 5.2 for the y-intercept, I want units, no naked numbers. Now, the units for the y-intercept are easy. It's this unit capital J. You may or may not know what that stands for. It stands for joule, but we're just going to say J right now. But what about the units of the slope? Well, remember, slope is rise over run, which means it's going to be the unit of our, or I should say the units of the slope will be the units of the rise, which is j, over units of the run, which is s, so my units will just be j over s. That's enough. So now, when I write the actual final equation, it should look like this. U is equal to 2j over s times t plus 5.2j. And I know you don't know what j over s and j mean. That doesn't matter. Remember, this is just an example. So what are our final takeaways for exploring relationships? We want to make sure you can answer these 3 questions with a yes. Can you distinguish between independent and dependent variables if you're given a situation? Can you organize data in properly formatted tables and graphs? And can you draw a best fit line and determine its equation if we have some sort of linear data set, keeping in mind that that equation represents the relationship between these 2 variables?